Okay, now I have written a little bit of stuff down, just summarizing what we've obtained over here. That for a delta L increment at 0, 0, 10 centimeters for the loop in the XZ plane with the current running counterclockwise, and I'm not sure I've said that, but the current's running counterclockwise, which is in this direction. The direction of the current at this point is the I direction. And delta L is delta L times I, and the R vector goes from the current segment, the I delta L segment, back toward the point at which we want to calculate the field, and that point is the origin. So here's our R vector. Okay, so now all we have to do, and our current's 50 amps, so we have everything that we need to plug in here. So it's very straightforward now. We got 10 to the negative 7th Tesla meters per amp times 50 amps times our I delta L, our delta L vector, which is our magnitude delta L times I, crossed with our R divided by magnitude of R vector. And I didn't write that out as clearly as I'd like to because of limited space when we did this in class. That's going to be our what? Negative 0.1 meter times K divided by the magnitude, which is 0.1 meter. And then this is over R squared. R, again, magnitude of R is 0.1 meter, so it's 0.1 meter quantity squared. Now a little simplification over here before we do any of the real arithmetic. 10 to the negative 7th Tesla meters per amp times 50 amps times delta L times what? I cross negative K. We got a unit vector here because, of course, vector R divided by its magnitude is a unit vector. And that unit vector is going to be negative K. So our cross product is going to be really easy. We're not going to write down the determinant to do I cross negative K. We're going to use our right hand and what we know about vectors. Okay, our denominator, of course, will be the square of 0.1 meter, which is 0.01 meters squared. So now what do we get? Our units, we're going to have units of delta L over meter squared. Now delta L is going to ultimately probably be in meters, but we don't have units on our delta L. That's part of our delta L quantity. So we're going to have meter over meter squared, and we're going to have amps over amps. So we're going to have units of, I'll write it this way, Tesla over meters, okay? And then it's going to be 50 times 10 to the negative 7th, which would be 5 times 10 to the negative 6, divided by 0.01, we're multiplying by 100 essentially, which is 10 to the second. So we end up with 5 times 10 to the negative 4th for our numbers. And then that's times our unspecified increment delta L. And then that's times the vector I cross negative K. Now let's see, I cross negative K is J. Okay? And that's the same thing, you know, we got in class, but maybe a little easier to read. Now, the thing that we really want to see, this is just one delta L increment. Okay, how do we calculate the field due to the entire circle? Well, we're going to partition the circle into little increments, and each little increment is going to have a little different direction, right? But in each case, wherever the increment is, we have an increment down here. The R vector would be here. So here's an R vector, and here's another I delta L vector. Okay, whatever its direction, it's perpendicular to the r vector. So when we do our I delta L cross r, we're going to be crossing, it's hard to get my right hand in the right position, we're going to be crossing this vector with this, okay, which is going to give us a vector straight out of the board. It's going to be the k vector again. Okay, these vectors are perpendicular. They're in the, I'm sorry, the j vector. They're in the xz plane, and the only thing perpendicular to the xz plane is in the y direction. So that wherever we are, our cross product is going to have a j. And our magnitudes are all going to be the same. I mean, you know, our whatever our delta L vector is crossed with our unit vector in the direction of r, we're going to get k. We're going to get j. The magnitude of delta L is still going to be just delta L, and we're going to have the same current, and we're always at the same distance, so r is never going to change. So for any increment anywhere around here, we get the same expression. Okay, so partition the circle, we get the same result for every I delta L increment. Again, because I delta L is tangent to the curve and r is back toward the center, so you know they're perpendicular. Okay, so what we get the total field is what? B equals the sum of all our delta B's. Now being loose with the notation, as physicists often are. I'm more in the math than I am in the physics, but I've got a foot in both. So I'll bring myself to be as imprecise as physicists often are when they're doing these things, because in physics you can get away with it. In mathematics you got to be careful about the theory. End of digression. Sum of our delta B's is going to be the sum of our, well, we're always going to get 5 times 10 to the negative 4th Tesla per meter times delta L times J. Meaning that this is a constant and J is a constant. We can factor that out of our sum. Now I know that you were hoping that we would take the limit of the sum and get an integral. And we will, but not this time because we don't need it for this reason. And I've got the summation sign out there where I should be writing what I factored out, which is the 5 times 10 to the negative 4th Tesla times delta L, times J. And then that is times the sum of our delta L. Well, what's the sum of our delta L? Well, our delta L's are the increments we get when we partition the circle, the length increments, okay? Well, we partition the circle. That means every length increment is separate from any other, but every bit of the circle is in one of the length elements. Doesn't that mean then that when we add up all the length elements, we get the circumference of the circle? So this is going to be 5 times 10 to the negative 4th Tesla times J, and it's Tesla per meter. I didn't write the meter here. I need it here and I need it here. Times the circumference. Well, the circumference is 2 pi r, right? 2 pi times the radius, because the definition of pi is ratio of circumference to diameter. So it's pi times the diameter, and diameter is twice the radius, so it's pi times 2r. Well, r is just 0.1 meter, so it's 2 pi times 0.1 meter. So that's 2 pi times 0.1 meter times 5 times 10 to the negative fourth Tesla per meter times J. Every little contribution here gives us a little more J. Okay, a little more magnetic field at the center in the direction of the J vector. Now, I could simplify that. I could do numerical approximation with pi. You see, 2 times 5 is 10. That's going to bring us up to 10 to the minus third, but it's times 0.1, so we're back to 10 to the minus fourth. So it's 5 pi times 10 to the minus fourth Tesla. There's our field at the center of the loop. You want to deeply understand this because you're going to be doing integrals that are based on this incremental process, this partitioning process. So you want to make sure you understand this and also understand how this will approach the integral, but the integral is going to be the integral of dl. Okay? You might parameterize the circle in terms of theta or something and d theta, but no matter what you do, you're going to end up with the integral equaling 2 pi times your 0.1 meter. Okay? The integral of your dl will equal your circumference.